So this project that we're working on is joint work between myself and Louise, and we just decided that just for this kind of first introduction that we'd I do basic talking for this one. So the Feynman machine, what is it? Most people not too sure. So just pop quiz. How many people have heard of a physicist called Feynman? Okay, keep your hands up, keep your hands up. Now, keep your hands up if you can answer this question. One person? No? No? Okay, the answer is Joan Feynman. Okay, actually, in her own right, a very eminent physicist. She was Richard's little sister, and she decided to become a scientist like her bigger brother when she was woken up at 5 o'clock at the age of 5, and they snuck out and to a golf course, I think near their home, and Richard showed her something like this, obviously not exactly the same, and she was fascinated immediately, and she decided to become an astrophysicist and find out exactly how these things worked. And she's still alive. She's 90 years old this year, and she just retired from the Jet Propulsion Laboratory in 2002, I think it is. So in between then, in 1963, Richard Feynman gave one of the first lectures as part of his famous series about chaos and the emergence of chaos in real systems. And he said this. So just the red words are probably the most important things. So this is obviously Rich Hickey loves several of these words. So the complexities of things can escape the simplicity of the equations. And perhaps nothing short of God is required to explain the complexities of the world. And the example he gave, possibly inspired by his sister who was studying the sun, he described a simplified sun, which was the only thing that worked at the time. The real sun, along with all its structure and sunspots and everything, are really in the equations. We just haven't found out the way to get them out. So, fast forward about 15 or 20 years, to the late 70s, and a discovery was made about chaotic systems. And this was that there is a way to get things out of not out of the equations, but out of the system itself. And what you see on the left is a dynamical system, which is the kind of thing that he was talking about, a chaotic system. And on the right is something that's mechanically reconstructed from a signal coming out of the system on the left. And this was turned into a theorem which tells you exactly how to do it and what mechanism to use and exactly when it works. And it turns out it works almost everywhere you look. And this is the same system that we'll see now both Joan Feynman used and also the Feynman machine uses. And basically you can ignore the details of the mathematics. This is what it means. It means that unlike what Richard Feynman was talking about, you don't actually need to understand the laws of motion, the equations, the differential equations, in order to build a model of a system. You can just get it from the data. And that's what that mathematics basically says. So about 10 years after that was discovered, one of Joan Feynman's most major papers was about the long-term dynamics of sunspots on the sun. And she was analyzing data like this, and she found some breakthrough information based on analyzing this using that type of mathematics. And down here at the bottom is this Takin's theorem, which is at the end of that paper. And that's also the basis of the Feynman machine. Okay, so I'm just going to give you a very quick overview of the idea of the Feynman machine, the principle of it. And we're going to talk just very briefly about our current software on which the rest of this is based. We're going to talk about some choices for bringing Clojure into the equation. Just a very quick overview of Neandertal which is part of the project, and then there should hopefully be some time to see some code and possibly some demos. Okay, so dictionary of just made up this afternoon. A Feynman machine is a network of intercommunicating nonlinear dynamical systems, which basically means little clockwork machines, which can adapt to predict their future inputs. It's also a theory describing how the brain operates at the level of brain areas, and it's a brain-inspired architecture for machine learning. So, now, just a word of warning, there is some serious graphics going to appear next. Rich Hickey would flip if he saw this. This is just look at the title. That's a translation of the Japanese on the left, right? Okay. So I thought this was the best version of the picture. This is a partial map. It's a landmark paper from 1991 of the visual cortex of the macaque monkey. Ours is actually about twice as complex as this, as far as we know. And this might even be worse. This is just the connection map as known in 2008, so it's probably twice as much as this, of just the frontal part of your brain. Okay, so that's just a rough kind of underground map of that. So obviously, if you're going to try and get inspiration from how the brain actually works, you're not going to start with something like this. So in traditional Clojure fashion, Ogma has essentially reduced it down to this. So, and this is actually single braided. It's really good. I'll show you exactly how that happens in a second. But at any one time, the information is just traveling along one path through this hierarchy. So this is a multi-level, it's a spatio-temporal predictive autoencoder. Just the technical terms. So essentially, there's a number of stages. So down at the bottom is where you connect to the world. And what it does is it takes in a stream of inputs, and it encodes them on the way up, and then it passes them across to the right-hand side, and it decodes them into predictions. So at each stage, predictions are being made about what the guy on the left is going to see next. And down at the bottom, every time step, you get a prediction of what you're going to see on the input side. So now this is the scary part for me. So this is live fig wheel powered quill. That is not supposed to happen. Bear with me a second here. That was not closed before. Sorry. Okay. Okay, sorry. Live demo. That was actually working perfectly a second ago. All right, I'm going to have to skip that to the end. I might try and get it in if we get time. What I'll say is that's what you do when you put that at the beginning. Anyway. Right. Okay. So if we go back here, what I was going to show you is just a quick demonstration of how each encoder works. For anybody who's familiar with how feed-forward neural networks work, it's broadly similar, but there are some big differences. So, for example, there is no backpropagation in this. It's all run off local prediction errors, which makes it dramatically more efficient. As well as that, we use a whole load of different optimizations. So, unfortunately, I can't give you a live demo of that, which is just a pity for the moment. I'll see if we have time at the end. Okay, so I'll just move on to the next part. Basically, as I was saying, the inputs come in, which are either just pure sensory inputs, or they can also be a copy of the current actions that the system has been taking in order to generate those inputs. And at each stage, there's an encoding of that, and that's passed up on the left-hand side to the top. And then it's passed across to the decoder at the bottom, at the top, and it generates a prediction of what's going to happen at encoder n at the next step. And then that's passed down and combined in the lower levels with the encoding coming over from the left. So the decoder gets two pieces of information, something about what's just happened, and something that's usually longer range, longer term. And that allows it to make it more, it's basically combining information from, there's information basically combined at every point that's originating from all over the network. And then at the end, it produces a prediction of what's going to happen next. And it uses the principles of Taken's theorem to effectively, each of these things and the whole thing together, and each of the levels and each of the encoder and decoder are all nonlinear dynamical systems that are really abstractions of brain areas. And they communicate with each other using sparse binary vectors, which you would have seen 2 minutes ago, which are very efficient ways of encoding information. And they allow you to do things like, for example, distribute these things across multiple computers and stuff like that. And it's very efficient, and you suffer no degradation in performance. Because all you're doing is essentially, you have a network of large mutable objects that are sending each other immutable sparse binary vectors, which can be compressed very easily. Okay, so that's the kind of architecture of the Feynman machine. And I'm just very briefly going to talk about the 2 technologies that we've built. One of them, Augmeneo, is from kind of about this time last year we released it. And eAugmeneo is our new version, which I'll show you a picture of a demo for, because I don't trust any of the I don't trust the internet anymore. And eAugmeneo was actually only publicly released 13 days ago. So, and this is really it. So both of them are essentially the same architecture as I showed you in the in the diagram earlier. And Augmeneo runs essentially large networks on massively parallel architectures like GPUs using OpenCL. And eAugmeneo is a pure C++ library, which just runs on your CPU, but it's optimized for low-powered hardware. So, for example, about 3 weeks ago, you can get this on YouTube there. If you just search for Raspberry Pi or just Augma Raspberry Pi, something like that, you'll see a video, which I'm not going to try and even show you now, of my colleague Eric. And that's a self-driving car, and the self-driving car learns how to drive on a Raspberry Pi on the car. And nobody's ever even tried that to our knowledge before, never mind succeeded. So he's now working on one that works on a Raspberry Pi Zero, which is the thing you get free on the front of a magazine for, I think it's like $3, $4, something like that. And I think we'll get that working sometime in the next week or 2. Okay, so the idea is that we're looking for something that's as powerful as the way that the brain learns, and something that's as efficient as the way that the brain learns. It doesn't require millions of examples. You can train this thing to solve a driving task by just giving it example driving in about 2 or 3 minutes. Okay. Okay, so we have a number of choices to build a Clojure version of this technology. And essentially this project is trying all of them. So the first version of it is to build a wrapper for the existing libraries. So we already know there's some serious engineering going into both of those. And essentially, it's just a matter of engineering and then putting an appropriate Clojure interface on the front of it. So this is really how that works. So we have Augmeneo and eAugmeneo as they were, and they come already with swig bindings that generate a rather verbose Java JNI interface. And the work that we've done essentially is just to create those wrappers. So, pardon me. Now, hopefully this will work. Okay, so this is the wrapper for eAugmeneo. And I don't know if you can read that, there's some light on the screen. But basically, this is just a set of pure functions that operate, a set of functions that basically translate maps and vectors and traditional Clojure data structures into the appropriate setters and getters for these mutable Java objects. So This one including a demo program. So that's an entire demo program there, that 30 lines. But the wrapper for eOgMNEO is 93 lines. Sorry, 85 lines, I think. I think step is the last one there. Okay, and then this is the wrapper for, this is the wrapper for eOgMNEO. And it's also about 85, 95 lines. So you can see it's doing something similar. And all it's really doing is just translating from the Clojure data, iterating over it, and then using these setters and getters. And just making sure that the Clojure that you write is a lot more idiomatic. So I'm not expecting you to read all of this. Most of that is actually just setting up data. And then calling these various helper functions, and then running the hierarchy inside the loop. I think it's actually 1, 2, 3. Line 1, 2, 3 is the this one here is the one that actually runs the network, and it just basically pulls out and just measures errors and stuff like that about the prediction. So the idea is basically that you can treat the thing as if it was some hidden data structure, and you just pass in Clojure stuff and get Clojure stuff back out of it. Okay, and the other strategy then is to re-implement augMNEO and eOgMNEO using Neandertal. So obviously this is a bit more ambitious, and we're in the early stages of this at the moment. But essentially what we want to do is we want to exploit the power of Neandertal, which is about as fast as you can get any Clojure code to run when you're talking about large-scale linear algebra, and keep the kind of idiomatic Clojure interface, but have the Clojure going as far down as possible before it starts sacrificing performance. Okay, so I'm just going to give you a brief. I don't know how many people are familiar with Neandertal. There was a talk last year about it from Dragan, who's a super genius, but I highly recommend if you have any kind of heavy numerical work to do and you want to use Clojure, this is really, really, I mean, it's a beautiful website, loads of documentation for all the libraries. Everything just works out of the box as long as you get it set up correctly. There's a few things which he warns about the Intel libraries, but once you get over that, it's happy days, it really is. It's fantastic. So we're concentrating really on kind of re-implementing the algorithms in such a way that we can reason about them and change them on the fly. And we're going to be doing that in Neandertal. So the demo that you would have seen, had it been working, actually is running live algorithms. It's not just a cartoon animation. It's actually, that's possibly why it crashed the browser. But it's actually running live algorithms from within Clojure script, from within Quill. So we're looking for obviously something more robust with Neandertal. So this is really a quick sketch. So this might seem familiar as kind of an architecture on the left that talks to OpenCL and an architecture on the right that talks to the CPU library. But he's obviously done an awful lot of engineering. Like, I really highly recommend taking a look at that. Okay, so progress so far, we have working wrappers for both eOgMNEO, which is only out 2 weeks, and for augMNEO. And we're currently building some demos using those. So, and we're going to be connecting up this Quill stuff to that. We're 100% sure that Neandertal will work, and what we're really trying to do is trying to identify how to get the algorithms into such a state that you can talk to them through pure data and get the underlying system to change how the algorithms work, because we want to use this as a test bench for developing new versions of the algorithms. Okay, now just trying to see where we are on time. Okay, we're good. Okay, some takeaways. The first takeaway, obviously, is that if you're interested in machine learning for some serious purpose, not just to find out about it, because this stuff is actually has quite an entry level, because it's essentially a combination of hard neuroscience, hard applied maths, and machine learning, and they're three skill sets that don't often intersect. But we've tried to package things up in such a way that traditional machine learning people can get access to it either through C++. The Python bindings are actually really good. And hopefully in the next month or two, we'll have the whole Clojure system working. And in particular, if you want to visualize and experiment with variations on the algorithms and then contribute back to those, we'd be delighted to do that, because everybody's problem may have slight tweaks to the way that the thing works. But it should be a very low-cost experience. And the last time I downloaded these things, it was literally just 20 minutes, and you'd be up and running. You'd be able to do demo programs and start writing your own ones. It's actually quite a good experience. So if you have a machine learning problem and you can't get any traditional approach to work, and your stuff has to do with things changing over time, your data has something to do with things changing over time, this is certainly something worth taking a look at. And if you do have such a problem and our technology solves it, then we'd really, really like to talk to you about how that would work. Okay, so, and then particularly for heavy-duty numerical work, I really recommend taking a look at Neanderthal, even if it has something to do with machine learning. It's a really good idea. Okay, so let me just see if I can get this thing up and running. 1 second now. Bear with me a moment, I'll just see if this is... It looks okay. Sorry, I'm not a fig wheel expert. Is that the right thing to connect into, or? Pardon? Yeah, I'll try that. No, that's the fig wheels error. 1 second here. Okay, very good. Okay, so this is actually based on a kind of thing. We've added a kind of a state machine onto the top of Quill. So each of these phases that you see in the top left corner is just going to show a different state. So it's like Quill in that you generate a state, and then you run pure functions to update it, and then you draw it. But actually each phase of this passes on the state it's made onto the next phase. And it's actually quite interesting. So this is a neural network. So on the left is an input layer that's just getting some data. And on the right is what we call a hidden layer, which is going to be connected to it. So we do that by connecting up a large set of weights that connect each of the elements on the left to each of the elements on the right. And you can see, I think, that the hidden layer now is updating in response to the inputs. Okay. So that's done with this is why you need linear algebra software. You have a big weight, these are tiny vectors. So you have a big weight matrix on the left multiplied by the input vector in the middle, and you get the output vector on the right. So one of the things that everybody does in neural networks is they impose a nonlinearity on the output. So they don't just take that, because that's just a matrix transformation, and you can just multiply all those together. So you have to put in a nonlinearity. But one of the problems with that is that the traditional deep learning people, they need everything to be differentiable because they have to do backpropagation. But if you don't have to do backpropagation and you're just using local prediction error, then you can do things like this, which is just a winner takes all. So I think if you see the histogram just beside the hidden vector, that shows you the values. And the blue dots are basically the top 5 of the hidden layers values. Okay, so you get the output vector is a big vector that's nearly all zeros and only a tiny number of ones. And the tiny number of ones is called a winner-take-all algorithm, or a k-sparsity algorithm. And this has huge advantages if you don't have to backpropagate. If you do have to backpropagate, you can't do this. But this is how the brain works, because it uses spikes. And so there's a whole lot of information theoretic properties of spiking neural networks that you can't do. You can't do with continuous real-valued variables. Okay, so that's how a very, very schematic view about how an encoder works. And the decoder works in a very similar fashion, except you just turn it around the opposite direction. And it generates a prediction given an encoding. So it just operates in the opposite direction. And sometimes we actually just use the same weight matrix and just turn it around. Okay. Right, so that's the end of that, just very quick thing. Sorry, the didn't happen in the middle, but okay, so apologies for the roundabout version of that. Okay, so thanks very much.